Today we will conclude our discussion on recurrent neural networks, and that conclusion will naturally lead us to the next network, the long short term memory network. We will also briefly discuss connectionist temporal classification. So far here's our development with the Lego blocks of modern deep learning, feature maps, kernels, strides, padding, pooling and so on. We have almost completed our discussion on RNNs, which are characterized by this back propagation through time. Today we will introduce the concept of a memory cell in LSTMs, long short term memory networks, and very briefly touch upon connectionist temporal classification. Later on, when we deal with unsupervised learning, we will talk of embeddings. So recap our discussion of RNNs for language modeling. We had a very compact representation for the recurrent neural network through a simple self loop on a neuron. The self loop was characterized by the weight WHH, the amount to which the hidden state at time t is determined by the hidden state at time t minus 1. The rest actually remained the same. You had WHX as a weight from the input to the hidden layer, and of course the output of this hidden layer did go onto the next layer HT. XT was the input at time t. What we have done here on the right hand side is unroll this network, the initial state of this network and the desired state of this network in its unrolled form. So both in the initial state and the desired state, the input x0 is m, x1 is a, x2 is c and so on. But what we saw was at the output layer, the prediction of the next character was a lot better with the desired state than in the initial state. The desired state should have been such that the next character predicted should have been an A when at position 0, and that was indeed the case here, and we were not nearly getting it that convincingly in the initial state. So we were able to get to this desired state mainly through back propagation. However, we discussed a problem with the back propagation setup. So recall that back propagation requires the derivative of the hidden state at say at time t with respect to the hidden state at time t minus k. Now this is proportional to the product over all the previous values. So index j equals t minus k plus 1 up to t of the partial derivative of hj with respect to hj minus 1. So this back propagation requires multiplication of these partial derivatives. This is primarily because we will never know the partial derivative of the hidden state at time t with respect to that at time t minus 1 directly. We will only know this or realize this through all the hidden states that are intermediate between t minus k and t. This multiplication is a problem, especially if these derivatives turn out to be less than 1. If each of these is less than 1, we will find that the product will vanish. If we choose the activation functions such that these partial derivatives are greater than 1, then of course we will have a multiplication of very large values. So this is the limitation, that we want to train on networks with long term dependencies. However, the influence of the given input decays exponentially as it cycles around the network through the recurrent connections. So this leads to the vanishing gradient problem. As pointed out, one might want to overcome this problem by using gradient values or choosing activation functions with gradient values greater than 1. That is, if you use an alternative function that gives value greater than 1, the problem will be exploding gradients. So solution is not simply in fixing the function. What can you do to overcome the vanishing gradient problem? So we will illustrate the significance of this vanishing gradient through an example. So let us say you were interested in the XOR of n binary variables, and we know that the XOR is 1 if and only if an odd number of inputs are 1, an odd number of the binary variables are 1, the rest should be 0. We are familiar with the construction of a finite state automaton or a simple logical circuit to keep track of this. So for example, with a logical circuit or a finite state automaton, the way you keep track of this is two states called even and odd, and every time you see an input 1, you go to odd, from even, or from odd you go to even, and of course we are interested in accepting those with odd. So for us the memory here is important, the fact that we have so far seen an even or an odd. What does not matter at all is what the inputs were prior to our current state. We actually need memory to store the current state, and in some sense we also want to forget inputs and the states prior to this current state. However, when you use the RNN to model such a function, such a XOR function, so let us say we have seen inputs for 7 time steps. Let us say we are interested in assessing the derivative of network with respect to input over a long time frame. However, this decays exponentially with time, and that is depicted here. There is significant update of input at time 1 with respect to the hidden layer at time 1. Go to time step 2 or 3 or 4, the effect is diminishing. Now is this of any significance for an example such as XOR? Well, no. All you are interested in is a cumulative number. Some of these states should matter, some should not matter. What actually should matter is whether you have seen even or odd. So remember that neural networks, or rather multi-layer feed-forward neural networks, which were motivated for XOR, but with all the sophistication so far, we fail for XOR of n binary variables. The motivation was for XOR of 2 binary variables, A1 and A2, but seems to fail for n binary variables. So what is the solution? Well, we could do several things. We could do gradient clipping, which means we do not let very small gradients transmit all the way back. However, what we will consider, which is more intuitive for the example that we have shown, is adding a memory cell Now the memory cell should be affected based on certain inputs and not affected based on some other inputs. So for example, at even if I see a 0, even number of ones, you see a 0 you remain here, or you see a 0 you remain here. So adding memory cell with gated inputs is what we desire. This is precisely what we refer to as long short term memory. So let us provide some more intuition for long short term memory. We have already stated our motivation and we want to illustrate our motivation through an example. So our first question was, is the ineffective long range update cost warranted? And here is an example. I live in India, I visit Mumbai regularly. So if the context India was further qualified using the keyword Mumbai, you could actually reduce the range of possible keywords that might occur next. So Mumbai, for example, certainly rules out occurrence of language keywords in a language such as Bodo. Bodo is a language that is spoken in northeastern regions of India. So in one sense, the occurrence of Mumbai should make the occurrence of India vacuous. Another motivation which we have built up through the XOR problem is, could we more meaningfully capture long term dependencies? Could we represent long term dependencies with better semantics? Here is another example to illustrate this point. So let us say I saw the sentence, or I am trying to model the sentence, I find movie X not too boring, and let us say I was trying to detect sentiment. So boring certainly would be indicative of negative sentiment. However, we note that the keyword like not, which also denotes negative, when padded with a negative sentiment, overall implies a positive sentiment. So could we more meaningfully represent these long term dependencies by capturing the state, the fact that we have already seen a negative negation keyword, and therefore anything that follows even with the negative semantics is actually rendered vacuous. Here is a demonstration of Alec Graves' cursive handwriting recognition, and what you see in the third layer here is the person writing, this is the actual writing. The actual writing is basically the x coordinate and the y coordinate of whatever is being written. So let us say this is a pixel, this is an x coordinate and there is a y coordinate. Along with that, the pen tip also has an orientation, so whether it is up or down, the direction in which the person is actually writing in the next pixel. The top layer here depicts characters as they are recognized. So what you can see here is M got detected only some time after it got completely written. In fact, O took a lot more time to be detected. there is a mistake here at V, it should have been an R. E took quite some time to get detected. So what you also see here is the output is being selectively presented at time intervals. So selective time instances of output presentation. An important point here is the output might get delayed, but it is never revised. So there is no correction here, it is just delay. What you see in the second layer here is what the LSTM goes through. This is the story of LSTM as it proceeds. So as already motivated so far, the basic foundation of LSTM is this memory cell, and the cell has some gates. It has an input gate, an output gate, and the cell's memory gate. What you can see here is at some time instances when output is actually presented, there is a sudden change of state, and the change of state is primarily marked by the fact that an output got finally or confidently predicted. The cell state changes based on what should be forgotten, what should not be forgotten. Some forgetting seems to be taking place here. Outputs are also presented selectively, so the output gate switched on corresponds to outputs actually being presented. Which of the inputs to be taking at all, for example a space here, should that be considered? Well, the input gate might get turned off when there is too much of white space. And as pointed out, the output gate turned on during the character predictions, which we see here when M or O or V or E get predicted. The memory gate gets switched as indicated in this intermediate layer. Finally, what we see in the fourth layer is the back propagation of the gradient. So certain predictions and certain cell state changes might have long term dependencies, whereas some of them might just depend on the immediate output. So for example, to predict that the A here has been correctly predicted, you just need to look at the previous time instance, whereas U might have its implications on its immediate neighborhood. So Fig, these have implications with respect to U, but may not be M and O and R and so on. So what you see in the fourth layer is the bits of the input, the extent to which they are affecting the probability that it's a character. So the effect actually has diminishing effect on the past. The direction of back propagation, needless to say, with respect to time. So here is the LSTM. We have a forget gate which influences whether the previous state of the cell should affect the current state and to what extent. So the previous cell state is Ct minus 1, Ht minus 1 was the output of state of the cell at t minus 1, xt is of course the input at time t, what you want to bring out at time t is ht at the output. Of course these inputs and outputs, all of them are also fed to the forget gate, and there is a small offset or a bias associated with each of these gates. So BF is the offset for the forget gate, and we applied a sigmoid activation unit here. So FT is what sits here. Similarly, we have the input gate which is affected by xt, ht minus 1, ct minus 1, the previous cell state, the output of cell at t minus 1 and the current input with its own bias Bi, and this is where you have the input state being determined, IIT, the input gate. So we learn the forgetting of previous cell state and insertion of present input depending on the present input, previous cell states and hidden states. Note that ht is the hidden state and also the output at time t. What about the cell state itself? Well, the cell state depends on the cell state at the previous time instance and with a tan H activation unit on the hidden state at previous time instance, the current input and an offset. But you shouldn't miss out that the IT, which was the state of the gate predicted on this slide, has its implication on the new cell state. This just means that CT will be affected by the previous hidden state, the current input and so on, only if the input gate is on. So new cell state CT is decided according to the firing of FT and IT. A lot of the effects here are being reflected through the so called Hadamard product. So CT is affected by CT minus 1, but there is Hadamard product with FT, and this is where the gating effect is taking place, plus IT times again the Hadamard product with a weighted linear combination of HT minus 1 and XT, let us call this ZT. On the other hand, HT itself is a Hadamard product of OT with a sigma function, the tan H function in this case, applies to CT. So this is where the gating effects are. Each gate is essentially a vector of cells and the weight matrix is maintained as diagonal, so that each element of the LSTM unit acts independently. The value of the output gate OT is basically a sigmoid function applied to the input at time t, the hidden state at time t minus 1 and the cell state at time t minus 1. One can pictorially visualize the effect of the input, forget and output gates depicted through the Hadamard product on the previous slide. So we can see that O is opening, so when the gate is opened it lets the information flow to the next gate. On the other hand, when there is a minus, the closing, the information does not actually reflect. Note however that all this is only the temporal unfolding of the network. In fact, it is a temporal unfolding of a single unit. And this is all done in the spirit of RNN that we have already discussed. So gradient information thus is also preserved. You do not unnecessarily backpropagate gradient when there is no need. It might be useful to see how the XOR of n variables gets realized through the LSTM, and in fact how backpropagation takes place. We leave that as a homework problem for you. Study an LSTM structure for XOR and look at the selective gradient backpropagation. Here we contrast the novel that is generated by an RNN when trained on a Shakespeare novel with LSTM, the novel that an LSTM might generate. It is interesting to note that the semantic coherence of words that get generated one after the other are not too high in either of these novels. However, what is interesting to note is a choice of vocabulary. So when it is the turn of Juliet to speak, you would at least expect terms that are common across Juliet's utterances to be coming up, and apparently that may be the case. So for second lord there is power and so on. For Lady Grey there is probably some keywords which are indicative of the person speaking. So this is where we see the short term memory in action. Is just the coherence of keywords with the turn, the person speaking. Of course, we have been talking about sequences, but sequence labeling itself is a big area, and there are several tasks in sequence labeling where the context is more important than the individual components and the exact sequence. Here is an example. So all of us, when we read the sentence, you can understand this tough aids and erroneous text, we all can understand the text is you can understand this though it is an erroneous text. Now how are we able to do this? It is because we are aligning not at character level but at word level. So this underscores the need to align at an appropriate level. And in this case we are more interested in aligning at word over say the character level. I mean, it is possible that the sound or image of individual characters is similar and the network might get confused if the context is unknown. In and M may look similar, this and this might sound similar. So as important as prediction is alignment in many of these real world tasks. So here is a broad range of sequence labeling tasks. We start with the simplest of them, the most standard. Given an input image M, you want an M, given an input image for L, you want an L. Slightly more complex is when the target sequence consists of multiple labels and segments of locations of the input is known in advance. So you are told that the segmented sentence on the input side has segments precisely coinciding with these square boxes as shown. These are known segments. And the output sequence therefore is based on the segments. However, we do not always have such data available, and segmenting such data can be very tiresome, sometimes even unnecessary and erroneous. On the other hand, many real world problems come under the third category, where temporal location of each label in the input does not matter as much. For example, as you're speaking, I might stress on certain vowels more than others, certain phonemes might get stressed more than others. So all you're interested in is the higher level view and not the details of how I spoke. I might speak the same sentence with higher speed or less speed. Different people can have different speeds of utterances. Also, the other example is if you had word images and the corresponding strings. So it's much easier to automate the process of segmenting the word image from a line rather than to segment the character images from a word. So this brings us to connectionist temporal classification. This is important especially when the length of label sequence happens to be less than the length of the input sequence. You are not trying to determine a one-to-one correspondence between input and output. So CTC label predictions can happen at any time in the input sequence. The other way of viewing this is that you actually predict the output at every time instance but perform some decoding of the output using probabilities we get at output layer in vector form. As an example, if you get the sequence MAACCC based on some stress that the speaker had on different characters and syllables, you can decode it to machine learning. So while training we will need to encode machine learning to this sequence, this is encoding problem, and while prediction we might have to go from this machine learning to and decode it to machine learning. So encoding is during training and decoding is during inference. Further, I have highlighted the intuition of CTC in this slide. So we have multiple possible utterances with each with probability. So P of machine learning and so on. What you want to do is decode during inference, and during training you want to encode, this is the other way. And the fundamental point here is that you have the probability of some label given the input sequence. Here L is this label, X is actually the input sequence shown below here, which basically corresponds to signals. But the way we are able to infer the right decoding is by looking at multiple probable intermediate outputs, which is what we call pi. So these form the pi's. Now the rest is simple, it's just marginalization. So we are basically going to look at probability of pi given x into probability of L given pi. Ideally it should be probability of L given pi comma x, but often what you do is you absorb this term P of L given pi into a delta function. So it's all the pi's that correspond to the label L. The problem of inferring the L given x as a sum is basically the subject matter of the forward backward algorithm. So there are dynamic programming algorithms, and especially algorithms that can make use of prefix tree structures, etc., to do this inference more efficiently. There is of course the other problem of how to learn these probabilities, these parameters, and that is again often done through maximizing of log likelihood. There are several toolkits for deep learning that are available online. You could look at Caffe, which is a very useful set of models for images, they are all convolutional. CXXNet, it's again a set of convolutional models which are simpler and often more efficient than Caffe. There is of course Torch, there is Theano which is Python based, there is Minerva, and what is also useful for students who want to make use of these models offline is this parameter server bindings to Minerva, Caffe and CXXNet that is available at this URL. Thank you very much.